Welcome back. So we're ready to determine the irreducible representations of Su2. So recall that to specify a n-dimensional representation of Su2, the only thing we really need to do is to determine three complex n by n matrices that satisfy this particular commutation relations. And it turns out that we can actually restrict our attention a bit further due to the following fact that may look familiar to you, which is saying that any finite dimensional representation of a compact Lie group is equivalent to a unitary representation. So just like for finite groups. So there we've actually proved it, and it turns out that the proof that we used to show that every representation of a finite group is equivalent to a unitary one can be easily adapted to the setting of a compact Lie group. If you remember from the first exercise sheet where you proved this, you were doing some operation where you were averaging some matrices over the whole group. Now, whenever you have an infinite group, but a compact Lie group, one can still do this averaging, but instead of summing over all group elements, we're doing an integral over all group elements. Okay, so we're not going to show this, but we can certainly take this as a fact. So if we're only interested in finding representations up to equivalence, so up to a choice of basis, then we may as well restrict here to unitary representations. So let's look at unitary representations of the Lie group. Now, if you remember, if you have a unitary group, then the unitarity property, it translates in terms of the generators into this the skew Hermitian property. So then the generators can be taken to be skew Hermitian. So that already simplifies the story a bit. Now we're a bit more used to working with Hermitian matrices, so it's of course easy to see that we may as well here look at Hermitian matrices. So let's say we define J of A to be an I multiple of the skew Hermitian matrices, then J1, J2, J3, they're complex n by n matrices which are Hermitian and satisfy now JA, JB. So you get an additional factor of I in front of the structure constants. So sometimes it's useful to work with the Hermitian generators, and actually in the physics literature one always does this implicitly. One typically says that the group element can be obtained not as the exponential of a linear combination of generators, but typically we already work with an I in front, such that the matrices that act as the generators are always Hermitian for unitary Lie groups. So we don't really use this convention in this lecture course, where we use the more mathematical convention without the I, but clearly here we are allowed to do so. And finding such a triple of Hermitian matrices is clearly equivalent to finding a triple of skew Hermitian matrices, satisfying this commutation relation. So to determine how we can choose these matrices, there is a very nice algorithm one can go through. And it's all going to be linear algebra from here on. And I'll go through this algorithm in considerable detail because it is kind of the prototype of what is happening for different Lie groups as well. And in fact, we will see that SU2 as a Lie algebra is actually present in all other Lie groups as a sub algebra. So we'll be able to reuse everything that we're doing here today for other Lie groups. In particular for the representation of SU3 that we'll discuss in a couple of weeks from now. Okay, so what are these steps? So step 1, it is what you would always do, for instance, in quantum mechanics when you're dealing with several Hermitian operators. You want to diagonalize them, right? But we know here that these operators, or the matrices that they have, they do not commute with each other, so we cannot diagonalize all of them simultaneously. But we choose a maximal number of them, so diagonalize a maximal number of generators. In this case, we can only choose one. In this case, only one, which by convention we take to be J3. By convention, taken to be J3. Right, since J1 and J2 are not going to commute with J3, we cannot diagonalize them as well. Okay, and here is a little definition. The eigenvalues of this diagonalized operator, so in this case J3, are called weights. And since J3 is a Hermitian, these weights are going to be real numbers. So they are going to be real numbers. Okay, so that was step 1. What is step 2? Well, it's called the highest weight construction. So let's write this, highest weight construction. So the name already tells what we're going to do. We're going to look at the weight, so the eigenvalue of J3 that has the largest numerical value. Okay, I'm skipping slightly ahead. This is actually step 3. Let me do step 2 first. So step 2 is really what we're going to do with the other two matrices, J1 and J2. And what we're going to do is we can take some complex linear combinations of them that turn them into raising and lowering operators. So introduce raising and lowering operators, or matrices if you like, as follows. So we write J plus minus to be 1 over square root of 2 J1 plus minus I J2. Now the first thing one should notice about these matrices is that they're not longer Hermitian, because I put the I in front of the J2. In fact, we see if we look at the Hermitian conjugate of J plus, then the sign here changes, so I get J minus, and vice versa. So why are they called raising and lowering operators? Well, it's because they're going to change the weights either up or down. So let's have a look. In order to see this, let's first compute the commutation relations. So the commutation relation of J3 with J plus minus is easily determined from here to be plus minus J plus minus, and the commutation of J plus with J minus is J3. So this means that if I have an eigenvector of J3, psi is an eigenvector of J3, so meaning that J3 psi is, say, m psi, where m is one of the weights, then I can apply J plus minus to this eigenvector, and the claim is that it's again an eigenvector, but with a weight that I shifted. So let's check this. So we're going to apply J plus minus to psi, and then see what happens when I act with J3 on this. So J3. And of course what we're going to use is this commutation relation between J3 and J plus minus. So this is saying that I get the commutator, so plus, sorry, the reverse order, say J plus minus J3, and then the result of the commutator, which is the right hand side here, acting on psi. And then since psi is an eigenvector of J3, I simply get that this is m plus minus 1 of J plus minus acting on psi. So indeed, the eigenvalue here, eigenvalue or the weight, is lowered or raised, or lowered. Now this is of course provided that this action of J plus minus on psi is not the zero vector. Because if it's a zero vector, we can't really interpret it as an eigenvector. Okay, so now we can really go to step 3, which is the highest weight construction. Highest weight construction. Which tells us that in order to explore all the vectors in our linear space, it is best to start from the eigenvector of J3 with the largest eigenvalue. Okay, so let J be the highest weight, and let's take one of the eigenvectors with this eigenvalue. There can be multiple, or we don't know at this point how large the the eigenspace is of this eigenvalue, but there will be at least one such vector. And j, one of the, let's say, normalized eigenvectors of J3. So meaning that J3 acting on J is J times this vector J. So really we're using kind of this quantum mechanical notation where we label the vector just by the value of its eigenvalue. This is just my labeling of this particular eigenvector that we have chosen. And we're assuming that we have some inner product, a complex inner product on the space, and that is normalized with respect to this. So this should be the inner product with respect to which the J1, J2, and J3 are Hermitian. Okay? Now the fact that J is the highest weight, it immediately tells us something, because we were saying that the raising operator J plus is going to increase the eigenvalue by 1, except when it annihilates the state. Now since we don't have an eigenvalue that is larger by 1, this means that J plus acting on this highest weight state has to vanish. So we know, because it's the highest weight, that J plus acting on this state is 0 by construction. So we know how J plus and J3 are going to act on this special state. So the only thing that remains now is to check what happens when I act with J minus on this state. Now J minus is going to lower the eigenvalue by 1. And let's just assume for the moment that it's not going to annihilate it just like J plus did. So it's going to give an eigenvector with eigenvalue J minus 1. So let's assign a label to this eigenvector. So we define J minus 1 by setting that J minus acting on J gives this eigenvector J minus 1, but we want to require that J minus 1 is actually normalized, so we put some normalization constant here, such that this is a positive normalization constant, and this second highest state is normalized. Right, as soon as we have this highest weight state J, then this really uniquely defines a second highest state, J minus 1. So let's compute for future purposes what this normalization constant n of J is. So to compute this, we do the following. So compute n of J. So what we want to do is we want to determine what is the norm of this state J minus acting on the highest weight state. So to compute the norm, I have to take the inner product of this state with its ket, if you like, so its Hermitian conjugate. So that is given by the following. Right, so I have to take the Hermitian conjugate of J minus acting on this side, and then by this formula here, this is nothing but n J minus 1 squared J minus 1 with J minus 1. Right, and this is 1. So if we can work out what this particular inner product is, then we know what the value of nj is. Oh, sorry, why did I write j minus 1? Let me remove this. The value of nj. Okay? So here we're going to use the commutation relation of j minus with j plus. Because what we're going to do, of course, we're going to say that the Hermitian conjugate of j minus is j plus, like this. And then we notice that if we would interchange the order of j minus and j plus, then we would have j plus acting on j, but that one is 0. So this is really the same as looking at the commutator of j plus with j minus, because only the first term in the commutator is non-zero. And then we can use the commutation relation, which says that this is j3j, but it was an eigenvector of j3 with eigenvalue j. So this is just j because this vector was normalized. So we conclude that this normalization constant n of j is square root of j. Okay, so we now know how to go from j to j minus 1 by acting via the lowering operator. Now what we expect is, if we now raise j minus 1 again, that we go back to j. So let's check that this is really the case. Okay. So next step, let's check that if we act with j plus and j minus 1, that we get something proportional to j. So what we can do is just put in our definition of what j minus 1 was. So j minus 1 was defined by this formula. So by definition, this is given by this formula. And now again I can use the commutation relation here, which says that if I interchange the order of these two, then I get j plus acting on j again, so for the same reason as before, that's going to vanish. So I can really just replace this by the commutator of j plus and j minus. So this is j3 over nj acting on j. But this thing, it had an eigenvalue j, nj was really the square root of j, so what we find is that this is just the square root of j again, times the highest weight state. Right? So I can go down to j minus 1, and then following j plus, I'm going up again. So it should be clear now what we're going to do to find many states in this this representation. We're just going to apply j minus repeatedly and find new states that are labeled by their eigenvalue, and then just see where this stops. Okay, so we continue. To define vectors or states of lower and lower eigenvalues by requiring that if I act with J minus on say some vector m, that I get an eigenvector. Okay, I'm just going to label the result of this application by m minus 1, where I choose the normalization constant positive as such that m minus 1 is normalized. So this one. Okay, so this gives me a whole sequence of vectors that are uniquely determined by our choice of highest weight state. And by construction, they satisfy J3 of m is m. So these are really eigenvectors of J3 with eigenvalue m. Okay, unless what I'm really defining, unless this is actually 0, unless. So at some point, I mean, if we're in a finite dimensional representation, we expect this to stop. So that when you act with some lowering operator on a vector, that it will just annihilate it. Okay, now my claim is, so this is step 4, if you like. I claim that these vectors, which are all orthogonal to each other because they are eigenvectors of J3 with different eigenvalues, that they actually span an invariant subspace. Span an invariant subspace, say W, of the n-dimensional complex space in which our matrices are acting. So let's see why this is the case. So recall from the last video that an invariant subspace at the level of the Lie algebra means that if I act with the generators on a vector in the subspace, that it's again in this subspace. Now we already know that if I act with J3 on one of these, well, it's going to be in it's an eigenvector, so it's trivially in the space spanned by these. And also by construction, J minus acting on M is going to be in this subspace. So really the only non-trivial thing that we have to check is that when you act with the raising operator on one of these basis states, that it's again a linear combination of these basis states. So we only need to check, that J plus acting on M is in W. So that's a linear combination of those. So let's just do that. And the easiest way to do this is by induction, if you like. So we're going to use induction. Since we know that J plus acting on the highest weight state, well, that's 0. So it's trivially in this subspace. But also that J plus J minus 1, it is a multiple of the highest weight state, so it's in there. So let's now suppose that J plus M is in W for some, let's say, M smaller or equal J. Then we're going to try to show that J plus of M minus 1 is also in W. So if that is true, then we can perform the induction, and we get that J plus acting on all the states that have weight smaller than J are in this invariant subspace. So let's compute this. Well, essentially the computation is the same as what we did for J minus 1. We're going to say that by definition M minus 1 is given by this, so 1 over n m J plus J minus m. I see I'm a bit inconsistent with the position of the pluses and minuses. Let me put them all downstairs to not run into any confusion with the Hermitian conjugate. Okay. And then we use the commutation relations. So this is 1 over n m times the J minus J plus acting on m, and then commutation relation with J plus with J minus, so plus J plus and minus, that was J3 plus J3 m. Right? And now we want to make sure that this is a linear combination of these states. But we already know by our induction hypothesis that this will be in W. Now, okay, this is just an eigenvalue, so here I guess eigenvalue m, so this is certainly also a linear combination, just a multiple of m itself. But we also knew that that J minus preserves this linear space, right? So this whole thing is indeed going to be in W. So that's nice. So starting from this arbitrary highest weight vector, we have constructed this sequence, and if I look at the linear combination, the sequence of vectors, then that is going to be an invariant subspace in my representation. So what does that mean if I actually assume that my representation was irreducible? This means that if my representation D that I started with is say n-dimensional and irreducible, okay, then it is not allowed to have any proper invariant subspaces. For you found a subspace, so the only option here is that it's not proper. And the only way in that a subspace can be not proper is that it's the zero space, but this cannot be the zero space because it has at least one vector in it. So then it has to be the full space. So that means that the span of these vectors has to be the full space, meaning that these should really be an orthonormal basis of Cn. And then j minus 1 is an orthonormal basis of Cn. That's really the only option. So as I said, I mean, this is going to be, oh, it looks like an infinite sequence, but it has to stop somewhere. And now we know exactly where it's going to stop. So in particular, it has to stop after the nth vector here. So in particular, if I act with j minus on j minus m plus 1, because that's the nth vector in this list, this has to stop. And it cannot stop earlier, because then I would have fewer than n vectors, so it could not be a basis. And another thing that this tells us is that this was not just some arbitrary choice of the highest weight vector. No, there is only one up to phase, if you like, highest weight vector in an irreducible representation. So in fact, up to an overall phase, this is a unique choice of basis that satisfies these properties. So what remains to do now is to compute what these normalization factors are. Okay, so let's compute that. Compute n of m. And there are two observations that we need here. So first of all, just by this fact, we know that if you act with j plus on some vector m, then this has to raise the eigenvalue by 1. So suppose that m is really smaller than j. So it has to be proportional to the m plus 1 basis vector. Right? And what else do we know? Well, we know that if we compute the inner product of this j plus m with this basis state, the eigenvalue m plus 1, we know what it's going to be, because j plus, remember that that is the same as j minus Hermitian conjugate, so I can let j minus act now here on the left hand side. And by our construction, we know what this is. We know that this is n m plus 1 times m inner product with m. So this is n m plus 1. So combining these two facts, we now know what the proportionality constant is. We know that j plus m is going to be n m plus 1 times m plus 1. Okay? And from this relation together with that relation, we can now determine a recursion for these normalization constants as follows. So we're going to compute now the inner product of the commutator of j plus and j minus acting on m. Now we know that the commutator of j plus and j minus is going to be j3. So what we have here is really m, because m is a normalized eigenvector of eigenvalue m. But I can also write this commutator out into the two terms. So I get that this is m j plus j minus m minus m j minus j plus m. But if you like, this is j minus dagger, and this is j plus dagger. So we have here the norm of j minus acting on m minus the norm of j plus acting on m. But okay, the norm of j minus acting on this is just going to be nm squared by our definition here, while the norm of j plus acting on this vector m by our formula here is going to be nm plus 1 squared. So this is nm plus 1 squared. So together with this fact that we know the normalization for the highest weight, m equals to j, this completely determines all normalizations. So together with n of j being the square root of j, this determines the solution to this equation uniquely, and it's a little exercise to determine what the solution is. Let me just quote you the answer. It is given by following formula. So let's see whether this formula makes sense. If, for instance, I act on the highest weight state, so if I do j plus on j, so this is supposed to be n j plus 1 acting on some imaginary state j plus 1. But if I put m equal to j plus 1, this actually vanishes. Right, so this is 0. So that's nice. But what is more, we can actually read off from this formula where the sequence is going to stop. Well, we know it's going to stop here, but we do not know what the relation between j and n is at this point. But now we can just figure this out, because where is the other 0 of this expression? So this second factor becomes 0, because raising the highest weight state gives 0. The first factor can also become 0, but that happens when m is equal to minus j. And this is exactly because of the lowering operator acting on the lowest weight state. And from here we read off that this lowest weight state is really minus j, because by construction this is n of minus j, minus j minus 1, if that would exist. But this is really 0 by this equation. So this must be the lowest weight state. So now we can conclude following. So the only assumption we really made that our representation is n-dimensional and irreducible. And we found this basis, and within this basis, I mean, the way that the operators j minus and j plus act is completely determined. So this means that any n-dimensional irreducible representation of SU2 is going to be equivalent to, well, essentially the representation that we just wrote down here, and it actually has a name, to the spin J representation and well, what is the dimension of the spin J representation? So it has states from J all the way down to minus J. So there are exactly 2J plus 1 of them, with n equal to 2J plus 1. Right, so n certainly has to be an integer, so in principle J could have been any real number up to now, but here from this we deduce that J has to be a half integer. So J can be 0, 1/2, 1, 3/2, etc. Okay? So this representation has an orthonormal basis of generators. No, sorry, the vector space on which it's acting has a basis labeled by n, and sometimes it's actually useful to denote the state by the pair of j, which really labels the representation, so the highest weight, and then the weight, where m runs from minus j plus 1 all the way up to j. And we've determined exactly how these operators act, such that, so let me copy that here. Well, these basis states are eigenvectors of J3, J minus lowers it with this normalization constant n of m, and J plus raises okay, and this is really the only thing that can happen. So in particular, for any dimension, there is really just one irreducible representation. Now, the only thing that we still need to check to fully classify the irreducible representations is to check that this spin J representation that we have found here is really an irreducible representation. Right? We've proved that every irreducible representation is of this form, but we also want to show that this form is really an irreducible representation. Otherwise, this would have been a bit of a vacuous statement. So that is the last thing we'll do. Luckily, it's not too difficult. So one has to check that it's really a representation. So it is indeed a representation. What should we do to check whether something is a representation? We should check whether the generators X satisfy the correct commutation relations. So check that X of A, which was related to J in this way, where, okay, so J2 and J3, they were these linear combinations of J plus and J minus. So to be precise, let's write them down. J plus plus J minus, and J of 2 is this way, and J3, okay, we're already told what the action is there. You can check that they indeed satisfy the commutation relations that they should for SU2. Just by plugging in these explicit expressions that we have for these operators J plus minus and J3. I mean, note from here that it's also easy to write down the explicit matrices for these operators, since these states M, they really just label, if you like, the columns in your matrix. So this is telling you that J3 is going to be a diagonal matrix with just these values M on the diagonal. The matrix J minus is, the only non-vanishing matrix elements are going to be on the subdiagonal, so where one index is M and the other index is M minus 1 with these values. And J plus is going to have non-zero values on the other subdiagonal, where M and M minus 1 are interchanged. So that gives explicit matrices, and you can check this. So then the only remaining question is whether it's irreducible, and actually this is quite easy to see too. It is irreducible. So what do we need to show again? Well, we need to show that it has no proper invariant subspaces, subspace AW. So let's see, how can we determine this? Well, suppose we have some invariant subspace W. Okay, so suppose I have this, and I look at some vector psi in this this subspace. Then, okay, in general, psi is going to be some linear combination of the basis vectors M, so running from minus j up to j, and then with some coefficient that maybe I'll call a sub m. And I know that if this is an invariant subspace, and I act with the operators j plus, j minus, and j3 on this, that it is going to stay in W. So let's be clever and act with the raising operator quite a number of times on this. So let's act with j plus on psi, and let's do this say k times. So what should we choose for k? Well, suppose that when I take m equal to minus j, that this is a non-zero quantity. Then I can raise it with j plus all the way to the highest weight. So this is going to be proportional to the highest weight state if I take k equal to 2j, I guess. Because all other coefficients of, say m plus 1, m plus 2, etc., they're going to be killed before the very last one is killed. So really by applying j plus a sufficient number of times, I can make sure that only one of these coefficients survives, and in the end it will be in front of the highest weight state, together with some normalization factors that come from this n plus 1 here. Okay, but if say the lowest one vanishes, then I just apply one less j plus and it will be the same. So you can easily check that one can always find a k such that this is the case for some k larger or equal to 0. But then I can lower it again, if you like. So j minus L times, acting on this, psi. So notice, so the fact that this is then equal to the highest weight state is telling me that this highest weight state has to be in W, because W was invariant. If I lower it a couple of times, then this is going to be proportional to the j minus L basis vector, which therefore also has to be in W for any L. So really, all the basis vectors have to be in W. Well, if all basis vectors are in some linear subspace, then this linear subspace has to be the full Cn, right? W is Cn, so it's the full space. So in particular, it's not a proper subspace. So we've shown that no, there is no proper invariant subspace of this representation. So the spin J representation is really irreducible. And this really finishes the full classification of irreducible representations of Su2. And they are the spin J representations, and they appear all over the place. For instance, in particle physics, we know that we have particles with spin, and these spins, the different states in the multiplet that a particle can be in, they really are the vectors in the spin J representation of Su2. And indeed, we know that spins come in half-integer values. Now later we will understand this a bit better when we notice that Su2 is actually closely related to the rotation group SO3. So these spins, they will also appear in, say, the angular momentum of particles. The angular momentum, recall, that appears because a system has rotational symmetry. So whenever we have rotational symmetry in a system described by some linear space, then it has to decompose into irreducible representation of SO3, and we'll actually see that these are also given by the same spin J representations. And as a final comment, what we'll see is that if we look at larger Lie groups like Su3 and study the irreducible representations of those, then such a Lie group will actually contain Su2 in various places. So we can actually use this classification of the irreducible representations of Su2 as the building blocks to construct the representations of more complicated Lie groups, in particular Su3. Okay, that's it for this week. See you next week.